All right, so this is forces on an inclined plane, and we've got a 6 kilogram block that's on a 30-degree angle. And this is what it would look like naturally. You've got an inclined plane, you've got a 4 kilogram block sitting there. We're going to find the weight of the object, which we already know is the mass times 10. So the weight's going to be 40, and we know mg goes straight down. Force normal is perpendicular to the surface, so it's kind of going up to the left. Force of friction is going to oppose the motion down. It also is going up to the left. So we're going to break gravity into its components so that we've got kind of going, it's balancing force normal and another component that's dragging it down the inclined plane. If you see where I did that real bold underline, that's the surface. So let's turn that surface so that it becomes horizontal. If we change our perspective, turn our head, then we would have force of friction going directly to the right, force normal going directly up, but then our mg is going to be going off to the left. That's okay for our perspective. Now, we will never draw this for a test for the free body diagram, but for our perspective, we can get everything vertical, everything horizontal. That way, we've got a component of gravity that's down, mg cosine theta, theta being the angle from the inclined plane. We would put it in directly into that free body diagram where I have it. On the opposite side, mg sine 30. Force of friction to the right. It is at rest, so we know we have balanced forces. Force normal up. We want to find the weight of the object. Of course, the weight is the force of gravity. That's a mass times g. G is 10 on Earth. So mass times 10, 40 newtons. We want to find the normal force. Normal force is balanced to the vertical component of gravity. Once we've turned these things, we can kind of see what's vertical. Mg cosine theta. So force normal is balanced with mg cosine theta. It's equal to it. Mg cosine theta in this case is 40 cosine 30. Put that into our calculator, and we're going to get 34.641. Force of friction is balanced. It's the only force going to the right. Mg sine 30 is the only force going to the left. Since it's at rest, that's a constant velocity. The leftward force balances the rightward force. Force of friction is equal to mg sine 30. Mg is 40, so 40 sine 30. Put that into our calculator, we should get 20 newtons. Because it's balanced. There's only two forces, one left, one right. They're equal to each other. All right, number 2, we've got a 4 kilogram object being pulled up the ramp by a string. The ramp makes 30-degree angle. Force of friction is 20. Since it's going up the ramp, now force of friction is down the ramp because friction fights motion. It's in the opposite direction of the motion. Friction is 20. It's going up the ramp, but it's slowing down. So if the velocity is up, but it's slowing down, that means acceleration is in the opposite direction. If the velocity is up and acceleration is in the opposite direction, that means acceleration, the net force, the larger net force, the acceleration is downward. That's going to be very important when we set up our net force equations. Again, I'm going to change my perspective. I want to see things horizontally and vertically. I hate looking at things at an angle. It's easier to see. We just cannot mess up our free body diagrams on our test because when we draw from dots, gravity always goes down. Don't mess that up. I've got mg going down into the left because that's how it's being pulled down the ramp. 40 cosine 30 is my vertical component of gravity. 40 sine 30 is my horizontal component of gravity. Force normal is balanced with the vertical component. My system, my net force, is going to be that 40 sine 30 plus the force of friction. Because it is slowing down, the net force is the downward portion, the leftward portion of the ramp. So that left side's bigger than the right side. So we're going to take the force of friction plus 40 sine 30 as the larger side minus the force of tension, the smaller side, is equal to mass times acceleration. Answering the questions, our weight, of course, is 40. Force normal is balanced with the vertical component, 34.641 newtons. In order to figure out what tension is, we have to do our net force is equal to ma. These are all the things we're thinking about when we put all this together. Force of friction is 20. The horizontal component of gravity is 20. So we're going to get that 20 plus 20 to the left minus the tension to the right. So we're going to add up the things that go together on the left and we're going to subtract from it what opposes it to the right. Because the acceleration is to the left, the net force is to the left, take the left minus the right. Force of friction is 20. 40 sine 30 is also 20, minus tension is equal to mass of 4 times the acceleration they gave us of 2. 4 times 2 is 8. So 40 minus tension is equal to 8. Subtract 8 to the other side, add force of tension to the other side, you get 32 newtons is the force of tension. All right, new problem. We've got a 6 kilogram mass being pulled up a ramp, 45-degree angle. The tension they gave us is 92. The acceleration is 5 up the incline. So tension is the larger force. The net force is to the right in favor of tension. Find the force of friction and the normal force. Okay, well, the normal force is going to be pretty straightforward. But we've got this 6 kilogram object being drug up a ramp. So we've got an idea of what that looks like. Force tension being 92, the acceleration being up. So I'm just making some notes in my picture. I'm going to change my perspective once I get everything drawn here. So I've got force of friction down to the left. I want to see this where the forces are horizontal or vertical. So I'm going to change my perspective. I'm going to turn my head to the left. When I tilt my head to the left, I'm going to see that my gravity is kind of going down to the left now. My component of gravity that's vertical is 60 cosine 45. It's the adjacent side. On the opposite side, the horizontal component, 60 sine 45. Because it's a 45-degree angle, these are going to give me the same solution. You can try it in a calculator, but a 45, 45, 90, two sides are the exact same length. 42.426. So the force normal, since it's not accelerating vertically, force normal is going to be balanced with that 60 cosine 45. One force up, one force down, they're equal to each other. We know tension is 92 to the right, friction is to the left, what we're looking for. Keep in mind, putting all these values here, this is for scratch work. This is how we work problems. You do not put values, you do not break into components when you're doing your test FRQs. Those are the ones on the dots. So our net force is the force to the right minus the collective forces to the left. And that's because it's accelerating to the right. We know the net force is to the right. We know the acceleration is to the right, all those things. That's equal to mass times acceleration. They told us tension's 92 minus the 60 sine 45, which is 42.426, minus force of friction, because we're distributing that negative into the parentheses, is equal to 6 times 5. Mass of 6, they told us the acceleration is 5. So 92 minus 42.426, I got is 49.574 minus force of friction is equal to 30. I'm going to subtract 30 to the other side, and I'm left with 19.574 is equal to force of friction once I add force of friction to the right side in newtons. All right, number 4. Number 4, I'm going to stop drawing the inclined plane just for a second because I can go directly to what it looks like horizontally. So I'm just going to go ahead and draw my MG down to the left. Do not do this on a test, just in our scratch work when we're trying to understand problems. MG is always down on a test when you're presenting it for points. So I've got mass times gravity, MG, going down to the left. My angle of the inclined plane is 30 degrees, so I can translate that directly underneath my free body diagram. The downward component of my force of gravity, because that triangle underneath my box is just showing me the components of gravity. It's not the actual inclined plane. The downward component would be 100 cosine 30. The leftward horizontal component is 100 sine 30. Normal is balanced with the 100 cosine 30. Tension to the right is 60, friction to the left. Net force is mass times acceleration. That is Newton's second law. Constant velocity means there's zero acceleration. I'm going to go ahead and show it as my rightward force minus my leftward forces is equal to ma. My force of tension is 60, but let's just go ahead and leave as force of tension for now. Force tension minus 100 sine 30, which is 50, minus force of friction is equal to mass of 10 times 0 for A. It's 0, so 10 times 0 is still 0, so we can just mark that as one big fat 0. So if we go ahead and put in our force of tension of 60, 60 minus 50, minus force of friction is 0, so add force of friction to the other side, do the math. 10 newtons down the ramp or down the ramp to the left, however you want to look at it, left and down are going to be the same thing. It's definitely not up or to the right. So down the ramp and to the left is our force of friction. Because if it says indicate the direction, go ahead and state it out. It's not going to hurt you. It takes 1 extra second. The last one, this is one that kind of trips people a little bit because it doesn't give us the mass. A lot of problems are going to not give us the mass, so we need to be very comfortable with this. Put mass in as m and see if you can cancel it out. So you got a small child, mass m, inclined plane 15 degrees. We know gravity goes straight down, but we're going to change our perspective so that we can see things horizontally and vertically. So let's turn that mass clockwise a little bit until it's flat, and we're going to see that we've got a component of gravity that's pulling it to the left, and that's the only force acting on it. Don't forget Newton's second law, acceleration's net force over mass is the acceleration. I think that's what I said. But either way, we need to know net force, we need to know mass, at least a variable for it. The only force acting on it horizontally, we're going to see is mg sine 15. Mg sine 15 is the only horizontal force, so mg sine 15 is our net force in the direction of motion. Mass is m, and that is equal to acceleration. Look at that, the masses cancel. G is 10, so 10 sine 15 is acceleration. Put that into your calculator. You get 2.588 meters per second square as your acceleration. How about that?